Hello and welcome to another lesson from Level Up Mathematics. In today's lesson, we will be exploring complex numbers and their operations. Now, in earlier courses, most likely in middle school, you learned about the real number system. And the real numbers, the set of real numbers composed of rational numbers, integers, whole numbers, natural numbers, and the set of irrational numbers. But all real numbers are also a part of a number system called the complex number system. And the complex number system is made up of real numbers and imaginary numbers. Now, a complex number consists of two parts, a real part and an imaginary part. When performing operations on complex numbers, the real part cannot be combined with the imaginary part. So here's an example of a complex number, a plus bi. The a represents the real part and the bi represents the imaginary part. Now, in our previous lesson, we learned that I squared was equal to -1 and that I is equal to the square root of -1. Those two facts will be very important for our lesson today. Now, the nice thing about complex numbers is when you're working with them, they're very similar to work with as just working with regular variables. So in example 1, it says simplify each of the following and write your answer in a plus bi form. So we have -3 plus 5i plus the quantity 6 minus 8i. So what you're going to do to add complex numbers is you're going to take the real part and add it together. So -3 plus 6 is +3. Then you're going to take the imaginary part. So 5i minus 8i, and that would give you -3i. Now, that's your final answer. You do not want to combine the 3 and the -3 because one is a real number and the other is an imaginary number. So that's an example of a complex number. Now, when you're subtracting complex numbers, you may want to start off by rewriting it as an addition problem to make it a little easier. So we have -4 plus 5i minus the quantity -6 plus 10i. So I'm going to rewrite this as -4 plus 5i plus, so I'm going to change this to addition of the opposite. So the opposite of -6 is +6. The opposite of +10i is -10i. Now we have an addition problem. And just like our previous problem, we added the real number part. So -4 plus 6 would give us 2. And then we added the imaginary part. So 5i minus 10i would be -5i. All right. Example 2, simplify each of the following and write your answer in a plus bi form. So in problem A, we have 4 times the quantity 2 plus 7i minus 3 times the quantity 7 plus 5i. So I want to start by using my distributive property here. 4 times 2 gives me 8. 4 times 7i gives me 28i. Then my second parenthesis, I'm going to multiply everything in it by -3. So -3 times 7 gives me -21. And -3 times 5i gives me -15i. Now, to simplify it, I'm going to combine the real number part. So 8 minus 21 would give me -13. And 28 minus 15i would give me +13i. All right, pause the video and try problem B on your own. All right, let's see how you did. There was nothing to multiply 2 plus 7i by, so I left it. And then we have to multiply the second parenthesis by -5. So this would be -15, and -5 times -8i would be +40i. Then I'm going to combine the real number part. 2 minus 15 gives me -13. And then 7i plus 40i would be +47i. All right, example 3. Find the following products and write your answer in a plus bi form. So here we're going to have to use the distributive property first. I'll take my first term, which is 3, and multiply it by everything in my second parenthesis. So 3 times 7 gives me 21. 3 times 5i gives me 15i. Now I'm going to take my second term, 4i, and multiply it by everything in the second parenthesis. So 4i times 7 is 28i, and 4i times 5i is 20i squared. Now I want to simplify this a little bit more. So I have 21, and then 15i plus 28i would be 43i. And then 20 times I squared. I should write this down for you. Remember at the start of the lesson we said that I squared is equal to -1. So this is the same thing as 20 times -1, which is -20. So let me circle that so you can see where I'm getting that. Okay. So 20i squared is equal to -20. Now, combine the real number part. 21 plus -20 is +1 plus 43i. All right, problem B. We have the quantity -6 minus 7i squared. So this is really -6 minus 7i times -6 minus 7i. So I'll start by taking -6 and multiplying it times everything in the second parenthesis. So -6 times -6, +36. -6 times -7i would be +42i. Now multiply -7i times everything in the second parenthesis. So -7i times -6 gives me +42i. And -7i times -7i would be +49i squared. All right, let's simplify this a little bit. We have 36. 42i plus 42i would be 84i. And we can simplify 49i squared. So we know that I squared is equal to -1. So 49 times -1 is -49. Again, let me just so you'll remember when you're looking back at these notes, how did you get -49? So I'm going to combine my real number part. 36 minus 49 would be -13 plus 84i. Now, in our next set of problems, an interesting result will occur when you're multiplying two numbers that are known as complex conjugates. For example, the numbers a plus bi and a minus b are the general form of complex conjugates. So let me show you what's going to happen, and some of you may be able to guess what's going to happen here. So we're going to multiply in example 4, problem A, 4 plus 5i times 4 minus 5i. So I'll start it out the normal way, taking that first term and multiplying it by everything in that second parenthesis. So 4 times 4 gives me 16. 4 times -5i gives me -20i. Then I'll multiply the second term, 5i, by everything in the second parenthesis. So 5i times 4 gives me +20i. And 5i times -5i gives me -25i squared. Now, hopefully you can see that in the middle here, the -20i and the +20i are going to zero out. So I'm left, when I simplify this, I'm left with a 16. This zeroes out. And Negative 25i squared will also simplify because we know that I squared is equal to negative 1. So negative 25 times I squared is the same thing as positive 25. And then you can just add those together. So 25 plus 16, 41. So notice we started off multiplying two complex numbers. To be more exact, two complex conjugates. And we ended up with just a real number. No imaginary numbers were left. Okay. Try problem B on your own. Try problem B on your own. All right, let's see how you did. We have negative 6 squared times negative 6 squared would be positive 36. And then negative 6 times negative 7i would be positive 42i. Then we had negative 42i. Then we had negative 49i squared. The middle terms canceled out, so we were left with 36. Negative 49i squared is equal to negative 49 times negative 1, so positive 49. So that would be 85. So again, when you multiply complex conjugates, you're going to end up with a real number. All right. Now, in example 5, it says find each quotient. So in all the other examples, we've been multiplying with our complex numbers. When we're dividing with complex numbers, what we're trying to do is we're trying to get rid of the imaginary number that's in the denominator. So to do that, in this first one, I'll multiply both sides, or both the numerator and the denominator, by 6i. Now, you'll see why we're doing that in just a minute. So I'm going to take this 3 and multiply by 6i, and then I'm going to take the 2i and multiply by 6i. So 3 times 6i would be 18i, and 2i times 6i would be 12i squared. Now on the bottom, 6i times 6i is 36i squared. Now, I know this can be simplified because I've got a lot of I squareds. And remember, we know that I squared is equal to negative 1. So anywhere we see I squared, we can replace it with negative 1. So this would be 18i. 12 times negative 1 would be negative 12. And on the bottom, 36 times negative 1 would be negative 36. Okay. Now, I want to rewrite that numerator. Because in a complex number, technically, we want to write the real number first. So I'm going to put the real number first, negative 12 plus 18i over negative 36. Now, if you were my student and you were to put your answer like that, I would probably accept it. Although I'm hoping you'll recognize that these fractions can be simplified because they all have a common factor of negative 6. So I'm going to divide everything by negative 6 and see what we get. So negative 12 divided by negative 6 would be positive 2. 18 divided by negative 6 would be negative 3. And negative 36 divided by negative 6 would give me positive 6. So if I rewrite this, I would be rewriting as 2 minus 3i over 6. Again, I probably would not be too picky if you did not simplify it all the way, but I want you to see what it would look like fully simplified. All right, let's try another one. This should say problem B. We have 10 minus 5i divided by 3 plus 4i. Now, this time, our denominator is a binomial. So to get rid of the imaginary part, we're going to have to multiply this by the complex conjugate, which is 3 minus 4i. 3 minus 4i. So on the top, we're going to start by multiplying the 10 times everything in that numerator. So 10 times 3 is 30. 10 times negative 4i, negative 4i. Negative 5i times 3, negative 15i. And negative 5i times negative 4i would be positive 20i squared. Now on the bottom, remember on complex conjugates, the middle two terms are going to cancel out. So really you only need to multiply the 3 times 3, which would be 9, and then the 4i times negative 4i, which would be negative 16i squared. All right, now let's simplify that. So remember, I squared is negative 1. And so let's talk about the numerator first. We have 30. Negative 40i minus 15i would be negative 55i. 20i squared would be negative 20. On the bottom, negative 16i squared would be the same thing as negative 16 times negative 1. So this is 9 plus 16, which is 25. Now I can simplify that a little further. 30 minus 20 is 10 minus 55i over 25. Now I'm hoping you will notice, again, if you left it like that, if you were my student, I would totally accept that answer. But I'm hoping you can see that all of those terms have a common factor of 5. So 10 divided by 5 is 2, 55 divided by 5 is 11, and 25 divided by 5 is 5. So this would be 2 minus 11i over 5. That would be the simplest form of that expression. And that concludes today's lesson, complex numbers and their operations.